Welcome to qnawire.
Okay, so we have a model car and it's controlled by a radio and it's moving in the X direction. The motion is directed according to the force displacement graph. This is Fx and this is N. X is M. And so the graph is divided into specific units, 1, 2, and -1, -2. That tells us that the force faces in different directions. The motion of the car is modeled by this specific diagram. So there's a triangle right there and then a trapezoid. Between a displacement of 0 and 3, we have a triangle, and then 3, actually 0 and 2. Between 0 and 2, we have a triangle. This is right here. And then this is 3. It goes all the way up until 4. Goes in the negative direction. That's the force in the a negative force. And then goes all the way up until, so this point is a displacement of 6. And then right here, it's a displacement of 7. So we're supposed to find the velocity of the car when x equals to 0.3 meters, when x equals to 4. Or rather not 0.3 meters, but 3.0 meters, x equals to 4 meters, and then x equals to 7.0 meters. So we're using the work energy theorem. The work is equivalent to the change in kinetic energy. So W equals to 1/2 mv final squared minus 1/2 mv initial squared. We're told that the car starts from rest when x equals to 0. So that means that this part of the problem will have an initial velocity of 0. So vi equals to 0 meters per second. And that means that the final kinetic energy will be 0. We don't have to account for that. We just need to find the work done in moving the car from the point 0 all the way up until the point 3. And that's the area of the trapezoid. Because remember, work is force times distance. The y-axis is the force, the x-axis is the distance. So we're going to do 1/2 times base, which is from 0 to 2. So 2 meters. And then times the height, which is 2 newtons. That's the energy expended from 0 to 2, or the energy required to move the car from 0 to 2. And then we also have the rectangle, this part, which is just the base times the height. The base happens to be 1 meter from 2 to 3, and then the height is 2 newtons. And so the total area, these two cancel out. We have 2 Newton meter plus 2 Newton meter. Remember, Newton meter is another name for a joule. So we have 4 joules. And then 1/2 mv squared, mv final squared. We want to find the final velocity. So that's v final squared equals to, if we divide both sides by 1/2 m, and this one is 1/2 m. Remember, the mass of the object happens to be 2 kilograms. So we're going to plug in those numbers there. This 2 comes up and changes that to 8. So we have 8 joules over 2 kilograms. That's the V final squared. And it's going to give us a velocity. It's going to give us a final velocity, 8 over 2. That's 4 to find the V final, we have to take the square root of that, so 8 joules over 2 kilograms, and that gives us a V final velocity of square root of 8. We're just going to do that with the calculator, so square root of 8 divided by 2, and that gives us 2. So 2 meters per second. Okay, it gives us 2 meters per second. So once again, let's just follow the steps. The energy required to move the car from 0 meters at the origin to 3 meters is 4 joules, and we have the final kinetic energy, which is 1/2 mv squared, mv final squared. And so that's going to give us V final is the square root of 8 joules over 2 kilograms. The second part of the problem is they want us to find the velocity, and I'm going to do that in the next page. So we want to find the velocity when x equals to 4.0 meters. Remember, if you look at the diagram, you notice it goes up and then goes down and then stops at 4. So there is no change in energy. So we have 0 joules between 3 and 4. So that means we still keep the same 4 joules from before. And 4 joules and then 1/2 mv squared. We're using the work energy theorem, which says work equals to change in kinetic energy. So work equals to 1/2 mv final squared minus 1/2 mv initial squared. The initial kinetic energy is 0 since the initial velocity, it started from rest, so initial velocity happened to be 0 meters per second. V final squared, 1/2 mv final squared. We divide both sides by 1/2 m and 1/2 m, so it's similar to the previous problem. So we have V final squared equals to these two comes up, and don't forget the mass, which is 2 kilograms, the mass of the car model. And so we have 8 joules over 2 kilograms. We get the square root of that. So V final is the square root of 8 joules over 2 kilograms. And that gives us a final velocity of 2 meters per second again. And that's the velocity at 4 meters. So this is x, and this is a force in newtons. So the velocity at 4 meters also happens to be 2 meters per second, and this makes sense because between 3 and 4, we don't see any additional energy. So we still have the same old energy of 4 joules that happen between 0 and 3 meters. So we're using that, and the object still has a mass of 2 kilograms, doesn't change, the mass doesn't change. The last part of the problem, we want to find, first of all, the energy from 0 meters to 7 meters, and then use that to find the velocity. What's the final velocity when x equals to 7.0 meters? So this is 0.0. We go back to our diagram. It goes up and then down up until 4. So this is from 0 to 2, and then 2 to 3, and then 3 to 4. And then between 4 and 6, it changes to a rectangle, and then it's flat all the way up until 7. This is the x-axis, the motion of the car, and this is the y-axis, the force involved. So first of all, we're using the work energy theorem, which says that work is the same as change in kinetic energy. So the same work is 1/2 mv final squared minus 1/2 mv initial squared. Our life is a little bit easier because the initial velocity was 0, so that's 0 meters per second. And so all we have to do is find the work, and we already know that the energy between 0 and 4 happens to be 4 joules. because this part was 4 joules from the initial part. You can see going back when we did the computations, we found out that the energy involved is all of that, 2 Newton meters plus 2 Newton meters. And then in the second part, the energy involved between 3 and 4 happens to be 0 joules because we don't have any changes in the force. The force itself, f of x, is 0. And remember, the energy is force times 0 times distance. Even if you're changing distance and your force is 0 newtons, you're going to end up with an energy of 0 joules. So that's the second part. The only thing we need to compute is the energy from 4 to 7. So we're going to do the energy from 4 to 6. It's a triangle. So 1/2 base is 4 to 6. That's 2 meters. And then the height is negative 1 newtons. So the energy becomes, these two cancel out. So negative 1 joules. The energy from 6 to 7, or the work done in moving the object from 6 to 7, happens to be 0 joules because we don't have any force acting over there. You see on the y-axis, the force at this point is 0 newtons. And if you want to find the work, you always do force times distance. So 0 newtons times 1 meter is just going to give us 0 joules. So this part gives us 0 joules. So we're summing up all the energy, the total energy, or the total work done from the beginning. So between 0 and 3, it's 4 joules, plus between 3 and 4 meters, it's 0 joules, and then plus between 4 and 6 meters, it's the area of this triangle, so that's negative 1 joules, and then between 6 and 7, that's right here, it's 0 joules. So the total work done, we just combine the 4 and the 1 joule, and we get 3 joules. We're going to use that in the work energy theorem. So we have 3 joules equals to 1/2 mv final squared. We divide both sides by 1/2 m, and this is also 1/2 m. V final squared becomes the same as this 2 comes up, algebra, so 2 times 3 is 6 joules, over the mass, which is 2 kilograms. So V final equals to the square root of 6 joules over 2 kilograms. 6 over 2 is 3. And using my calculator, I'm going to take the radical. So this is square root of 6 divided by 2. And that gives us 1.73. So the velocity at x equals to 7 is 1.73 meters per second. So just a quick recap of the process in finding the velocities at specific points. The first thing you have to do is to remember that you find the energy, the work done in moving the object from 0 to 3, and then from 3 to 4. Initially it's from 0 to 3, and there's a triangle on the rectangle. So finding the areas of those two is going to give you the work done in moving from 0 to 3, because the y-axis is the force and the x-axis is the distance. By definition, work is force times distance, and we got that energy to be 4 joules. We compare that to the work energy theorem. The initial energy, the initial kinetic energy, happens to be 1/2 mv initial squared. The initial velocity is 0. So we're canceling that out. This is going to be 0 energy. So V final, as you can see, is just the square root of 8 joules of 2 kilograms. And that gives us 2 meters per second squared. In the second part, the final velocity is going to remain the same because we don't have any work expended or expended between 3 and 4. It's 0 joules. So we have the same velocity, nothing changes because there's no work input going on. And then in the last part of the problem, we have to find the energy at each section of the displacement. So displacement from 0 to 3 is 4 joules, from 3 to 4 is 0 joules, from 4 to 6 is -1 joules because the force is going in the opposite direction. And then between 6 and 7, it's 0 joules. We do the math. The work energy theorem cancels out the initial kinetic energy, which is going to be 0. And so we're only left with the final kinetic energy. We use that. Compare that to the total work we got. The total work was 3 joules. And so after the math, we get a final velocity at 7 of 1.73 meters per second. Hope you enjoyed the video. Feel free to share any questions, send any questions out, and looking forward to the next problem, and enjoy your day. Okay, thanks. Bye.